Well, good morning. It's 9 a.m. Not sure about the sound. Can you hear me? Thank you very much. So let's quickly refresh our current topic, staining waves generated in different environments. So this is an example of several modes or harmonics generated in a tube or a pipe with both ends open. And a similar situation happens when we have a string and both ends of that string are fixed, attached, can't move. For that string, we have also a way for calculating the speed of pulses or waves traveling on that string. And several modes of a staining wave on a string looks like this. It's a handy practice, convenient practice, drawing modes and being able to quickly identify which picture represents the mode number 1 or which picture represents the mode number 4, etc., etc. And equations for both situations mathematically absolutely identical. Same set of equations as we have derived yesterday, but a different set of modes is being generated when one end can't move, is fixed, and only second end is free to move. So in that case, to generate stable staining wave, we should excite modes which have an odd number of quarters of wavelength inside that tube or pipe. And this is just a summary. Of course, basically, if we want to apply correctly a set of equations number 1 or a set of equations number 2, all we have to know is to recognize what type of a device is being used. So we just have to imagine or actually literally see the ends. Open ends, we call it an open pipe. What do you think is this? Open or closed? There's a piston right here. So it is closed at one end. And people say closed, but they mean at one end, and second end is free. You just have to generate the sound inside. What about this one? You can see through, open. This one, closed. What about this one? Open or closed? Closed because this end. And what about this one? That's not a pipe, so we cannot say closed, but we say string with ends fixed. Yeah? And we know that if we change the tension, we can adjust the fundamental frequency. Well, we can adjust all frequencies, but we can hear only the fundamental one. So we just continue solving different problems, doing some examples. Question, what do you think about this situation? Have you seen it? You can buy it, not from me, from eBay. A xylophone. So the length is related to the fundamental it generates. If you look inside, closed, closed, but there's a hole right here. So what kind of a pipe is that? What set of equations should we use for the xylophone? And of course, you can try to sketch the first mode, the fundamental, and see how it looks like. And that gives away the answer immediately. Why do we need the whole? Well, so we could generate a wave inside. And when we hit this metal plate, it actually excites many different sound waves. And those sound waves excite the air inside the pipe, but not all of them are equal. Those which do not satisfy a certain set of equations just die out very quickly. Only fundamental lasts long, and we can hear it. And what do you think? What set of equations should we use for those sound waves? You're not sure? Ask a question which would help you to make your mind. So if you're not sure, that means some information might be missing. So, and the best way to get the information is ask a question. You can ask it to a live person. You can ask it to the internet, but that's the only way to move. Or you can guess, of course, but we know not really helpful. So what did you say? Not sure? What did you say? 2. I like 2. There's no motion here, there's no motion here, but there's supposed to be motion here because any standing waves, a generic profile of any standing waves looks like this. So if we have no motion, we call it the node and another node, the shortest part of a wave which fits this tube, looks like this. And this picture represents a standing wave generated on a string. So the medium is the different, air, not string, but the set of waves which we can generate is the same. So we have to use the same set of equations. We have to count halves. Yeah. This is the lowest. And the next one would have exactly one wavelength fit, and the next 3 halves, etc., etc. Well, let me ask you about this. This question is directly related to this experiment. We can generate several modes. We can measure the frequencies, and you will be measuring frequencies of sound waves generated in different sources, including this one. All you need is a microphone and either oscilloscope or another measuring device. First step is to choose what set of equations you need to use, and here it's already given to you. It's an open pipe, so we have to count halves inside, and halves means use the equation with a 2. And of course, if we need to calculate the 9th or any other mode, first we need to get the fundamental. That's the question you have to answer. And to answer that question, you have to solve this problem. So you have to start writing something in your notebook. And 175 hertz. Do you think it's a fundamental? Well, we don't know. If we don't know, we can't make any assumption. So 175, if it's not a fundamental, what harmonic is it? Do you know? Can you tell me? We actually can say the number for this mode. And that's the nth mode. That's all we can say about it. We don't know what n is equal to, but we know it's nth. So the mode number n should have this frequency. And the next one. Now, you should say, what would be the number for the next mode? What do you say? Yep, that's how we count. If it starts from n, and here, this, what we call translation. We made it translation from text to, well, symbolic representation of what is happening. But for this particular pipe, the equation which relates the nth frequency and the fundamental one, is very well known. Well, now. And we can write this equation twice. You just have to write it accurately. So, what should you write here? Like this? Absolutely. And trust me, I've seen people forgetting using parentheses. And that would be wrong mathematically. But now, all right, we have equations. We can solve them. What would be the easiest way to solve these two equations? And that's what you have to answer to yourself. Solve the equations and pick a number. This is the first equation, right? And this is the second equation. In fact, we have two equations and two unknowns. So mathematically, it's absolutely solvable. But we don't, all we need is F1, the fundamental frequency, the frequency of the fundamental mode. Did you find it? What stops you? It's a matter of writing now, right? So we are solving these two equations. We need to calculate the fundamental frequency. That's the goal. And then you should enter your answer in a WebAssign. And I want to check what is happening over there. And in the morning, the screen went dark. I had to fiddle with it. So there is a chance system might fail, but I have a backup. Always have a backup. And a backup for the backup, which I also have. So right now you don't need the screen anymore because I'm pretty sure you already have all the information transferred from the screen into your notes, right? And we already have lots of answers here. Oh, no, that was number 2. This is number 3. Not many, wide distribution. So let's wait a little bit longer. Mathematically, what would be the easiest way to solve this directly for F1? There is mathematical operation. It has a name. Yeah? How do we call it? Substitution is not what I mean. We could do a substitution that would be a slightly longer way to solve this. if you want to get rid of f1 and leave only n, you can divide this equation and f1 getting cancelled. But if you want to keep f1 and get rid of n, what can you do? What do you think? That will work. But the fastest way is do subtraction. You're adding n to something. So if you subtract, it getting cancelled. 245 minus 175 should be equal to n times f1 plus f1 minus n times f1. That's not just correct way to solve it, because there are others, but this is the fastest way to solve it. So what do we get? That's it. Any questions, please? So at first it might seem that we don't have enough information, but again, we know what to do. First, we have to believe that we do, and then just power through, and eventually 99 times out of 100 get the result. Well, and if we multiply by 9, we get the 9th mode, or any other mode now is available. So next question about a different type of wave. You know, we count modes, first, second. We also count modes like first, next, next after the next, etc., etc. This one, this is not the first, this is not the fundamental. Which one is that? And again, so right now, you already either entered your answer or you copied the picture. Right now, you know the pattern for your answers. If you think it's the first mode, so you select 1, second mode, 2, etc., etc. And I want to go to this, back to this picture, because the answer is here, right? What do we count for standing wave generated in a pipe with open ends, or standing wave generated on a string with fixed ends? See? The third mode, 1, 2, 3, 3 antinodes. First mode, 1 antinode. Here, what do we count? Well, we call them first, and that mode has a name. How do we call it? Second? No. We should call it next, and we call it third. And the best way count how many quarters of a wavelength fit. The first mode fits 1 quarter, third 3 quarters. So for this picture, what should you say? What did you say? Let's count. So we know that the distance from a node to antinode is equal to 1/4. So again, this is a standard, generic, general profile of any standing wave. It should be a little bit more beautiful, more symmetric, but still. And we know the smallest meaningful part of a wave is 1/4 of a wavelength. And it's always a distance from a node to an antinode. So node, antinode, node, antinode, node, antinode. 1, 2, 3, 4, 5. fifth. And these two boxes say something about terminology people use, yeah? Between and in. So if you ask to count between the ends, that means inside, you see two antinodes. But if you count in the pipe, the antinode at the edge of it also should be counted. That's it, terminology. Okay, since we talk about pipes with one end closed and another end open, we can ask a similar question. Let's say you have succeeded in generating several modes, and those modes are 175, 245, 315. We need to calculate again the ninth, wherever, because anyway, we have to start from finding the fundamental, the first, the lowest. So please take a moment. And apply the same strategy we used recently. Calculate the fundamental. Feel free to discuss it with your colleagues. You don't have to whisper. You can be louder. I'm going to use this time to meditate. Three of you are always together, but why don't you talk to each other? You should consult with each other on the problem. What did you enter already? Same as before. The same as in previous problem. No. Well, 4 is 70, and 70 was the frequency which we have found for the pipe with both ends open, right? Now we closed one end. So something should be different. There shouldn't be the same frequency. I don't know if the microphone works. So there is clearly at least one answer which you shouldn't choose. 70. We have a different pipe. Yeah, it was the first pipe was open on both ends. This pipe is closed on one end. So and again, we know that the frequency should change if that's what open, close. It should change. So not 70, but what? Open, closed. These are the equations. We don't really have to make a choice what set of equations to use. They're given. And again, we can write that the mode number n has a frequency of 175 hertz, and the next mode, 245 hertz. The only question is, what is the next mode? What is the number for the next mode? What is the number for the next mode? What do you say? Why? Exactly. Thank you very much. That's exactly what we have to remember about this type of pipes. And that information wasn't presented, but you should remember it. N cannot be equal to any even number. So it could be 3 or 5 or 7, but the next supposed to be another odd number. So 3, 5, 7. So now odd numbers go by 2. So this is n times the first mode, and this is n plus 2 times the first mode. And of course, don't forget parentheses. And of course, now we can do the same mathematics. If we do subtraction, 70 will be equal to 2 times frequency, which makes it 35. Which is consistent with our experiment. Any questions? We just need to remember how we count modes in different types of, well, situations. Now, a standard problem, actually a standard demonstration, but it takes time. So what is happening here? We change the air column. We can do it differently. We can move a piston like in a trombone, for example. Or in this experiment, that was classical experiment, which has been used actually more than 100 years ago to measure speed of the sound. If you hit the tuning fork and bring it close to the open end, and then let water level drop, you just move that cup higher and lower, and eventually you reach a certain level when the sound becomes really, really loud. So loudness changes when it drops from ooh. That's it. Now you remember. Now, it happens only at a certain heights. There's the first, then second, and third, if the tube is long enough. So what do we have here? You hear the loud sound when the water level is, we'll call it H, 20 centimeters from the top, 0.2. Then 70 centimeters. Okay, so it goes down. All right, I want to redraw it. Oops. Make it. So tube, first time it reached at 20, H1, and the second time it reached at 70, H2, 0.7 of a meter. So we use the tuning fork which generates the sound with this frequency. All right. Well, now we have to make a choice. What set of equations should we use? What should we count? Halves or quarters? Well, what do you think? Well, naturally, at the top, we always will have an empty node. When we hear a very loud sound, that means a stable, steady wave is being generated in it. But what about this or this? Closed. So, set of equations, well, first of all, Fn equals F1 times n. Well, we don't really need it, probably. Now, that's a node. So a standing wave can be presented by like a rope-like profile like this. an empty node, a node. What's next? Well, it should be another empty node and another node. And what is the distance between these two nodes should be equal to? The distance between two nodes in any wave is equal to what? Again, it's handy to sketch a generic wave profile. Empty node, node, empty node, node. A standard measure, one more, an empty node. A standard measure is a wavelength. And the distance between two nodes will be equal to what? Someone has to say something. Thank you. Exactly correct. A half of a wavelength. That's it. So we can immediately make a conclusion from this picture without actually using any equation so far, that a half of a wavelength should be equal to the difference between these two measures. And that gives, that's 0.7. A half of a meter. That gives a half of a meter. So the wavelengths will be equal to 1 meter. And wavelength, speed, and frequency are related. Yeah. And that gives us 1 times 340 meters per second. On average, speed of sound under regular conditions close to 330, but it also depends on temperature and pressure. 340, 320, even 300 for convenience can be used. Any questions? Sure. Seeing is helpful. All right. This is an example of a problem when we excite a string in a certain way. The amplitude. Well, when we say the amplitude of a wave, we mean the amplitude of a very specific point. It's not this. Well, this point doesn't move at all. That's the node. This point moves within these limits. But the maximum span is provided by empty nodes. And that's what we call the amplitude of a wave. The amplitude of an empty node. And turns out it's 6 millimeters. Question is, if you look at this point, any antinode point, it should be, because antinode, that's missing. If you look at this particular point, it moves, it travels distance, and if you wait exactly a quarter, what distance will be traveled by this point, point P? That's the question. And of course, the pattern is clear. If you think it's 1 millimeter, you select 1, 2 millimeters, you select 2, etc., etc. So by now, you should make your mind and enter your answer. And I want to see it. So this question technically is not related to waves. It's related to our knowledge of simple harmonic motion, because this point, this antinode, this antinode moves up and down like a ball on a string. Exactly the same type of a motion. Equilibrium. If we release it from rest, it goes down, up, down, up. So, and we know that by definition, if we start from here and count when it comes back, that's what we call one period. That is what it is. And I need more than 15. So take a picture, mental picture, make a decision, enter your answer. I clearly see more than 33 people in this room. Let's break 40 at least. All right. And every time we get more and more answers. 6, which is absolutely correct. We just count. So again, how many quarters in a period?
4.
Exactly. So we count 1 quarter, and this is the distance traveled in 1 quarter, and that's exactly what we call amplitude. So if I ask you, what will be distance traveled by this point, the antinode, in 1 period, what should you say? Distance traveled can't be 0. Not displacement, distance traveled. That's actually, again, important difference, distance and displacement. Yes, in 1 period it comes back, so there is no displacement, but distance did travel. So what distance?
12 millimeters.
6, 6, 6, 6. That's how we count. It takes 1 period to travel 4 amplitudes. It takes a half of a period to travel 2 amplitudes. That's it. We know that a standing wave represents a composition or addition of 2 traveling waves. So this amplitude A, the amplitude of a standing wave, should be a composition, a result of addition of 2 waves traveling with the same amplitude. I just call them right and left, but it's supposed to be the same. This is the amplitude of traveling wave. But if we add them up together, we know we should get the amplitude of this wave. So amplitude plus another should be equal to 6. So the individual amplitude should be equal to 3, a half of that. That's it. Just a review of the fact that every standing wave is actually a result of a composition of 2 traveling waves. All right, just did it. Now, a specific example. So we have a lot of information here. The length, linear mass density, frequency generated, and so what does this mean? Sequence of images. Well, it means we roll a camera and then we look at several snapshots. We can assume that initially at t equals 0, this line represented the profile of the string. Then this instant is between less than quarter of a period, because in a quarter of a period it should be a straight line, and then the next profile, oops, too much, and then the next profile. So these are several pictures related to several instances. We don't really need all of them, we just need one to figure out, for example, what mode do you see? So this profile is the mode number harmonic. If you want to say something, just say it. 3. How do I know? Well, for this particular wave, I count halves or antinodes. I see 3 halves, 1, 2, 3, or I see 3 antinodes, 1, 2, 3, and so this is the third mode, which is supposed to be equal to n times first, or 3 times first, or it gives 1320. So we immediately can calculate the fundamental. 1320 over 3. No, 440. Yeah, Y6, I don't know, 440. Well, we can calculate what? Wavelength. Wavelength comes from the picture and from the fact that the length of the whole string is equal to 75 centimeters. So that's the length of the whole string. So the wavelength, which is this, will be equal to what? Well, fastest way, just do this. 75, if we divide by 3, we get a half, and then times 2, we get the whole wavelength. So 50 centimeters, right? Or a half of a meter. Speed, yeah, since v equals f times lambda, we just have to, yes?
Why is the wavelength not the area in between the two? The area, one curvature up, one curvature down?
Well, first of all, it cannot be area.
Sorry,
The wavelength, by definition, is distance, the shortest distance between 2 points with the same displacement, 2 points moving in phase. It could have been any 2 points. I measured from this node to this node, but we could have measured it from this antinode to this antinode. It doesn't matter how you measure it. You could have measured or find a quarter over wavelength and then multiply by 1, 2, 3, 4, 5, 6 quarters, right? So, and for the speed, we're going to get, well, I want to use f3 times lambda 3, so 1320 times 1/2. 660, 13 over to 6, 12 over 660 meters per second. So I'm just going with the wind. Yeah? Wherever I can calculate, I just calculate it. And what else can we calculate now? Well, we know for the string, the speed is related to the tension. So the equation which relates these variables is this. This actually confuses people because in this equation, capital T means tension, but also it's assigned to a period. So maybe a better way to write it like this. And this variable mu represents the density, mass over length. In this situation, we already know mu. So we just have to solve it for tension. So speed squared times mu will be equal to the tension, which means force of tension will be equal to 660 squared times 80 grams per meter. So we 0.08 kilograms per meter. Well, please tell me the result. Well, that's supposed to be newtons, so we can write shortly kilonewtons wherever it. All right, and we have answered all questions. We have found everything. Any questions? Now, instead of a free-standing wave, we can imagine we actually attach a vibrator, a function generator, which keeps this string moving at the same frequency, see, or the same period. But we can change the tension using different means, and the question is, how should we change it to change the profile, to make it the second mode? Well, so speed is equal to Fn times lambda n. And that's actually not I want. This is what I want. I want this tension mu, and I want it twice, right? Before and after. Before, and after we changed it, after. This doesn't have a subscript. We don't change the density. It's the same string. And also, we keep frequency the same. Again, why can we do that? Well, it assumes that we actually have some function generator which makes it vibrate with the frequency of the function generator. This is a case of a driven wave. And so this is the fact. And I want to divide these numbers. So I want, what do I want? since frequency is the same, this is what I want to do. F and B equals F. Actually, that should be probably a different letter. M, A. So speed before divided by wavelength before should be equal to, supposed to be easier way. Yes, there is an easier way. That's supposed to be n times frequency. That's supposed to be m times frequency. And that's the third mode. That's the third mode. How do I get to the?
We already calculated the harmonic.
Hmm?
We already calculated the fundamental.
We'll recalculate the fundamental. And okay, so we can know it. And so this is the known number. And that's supposed to be 2 times the new fundamental. So we can calculate the new fundamental. That's supposed to be a known number. And so that gives our new period. Oh, actually, that's what I'm missing, the new picture. The new picture should have only 2. So that's supposed to be the new wavelength. So we know the new wavelength after that's supposed to be equal to a half of the length. And if we know wavelength and if we know frequency, we can calculate the new speed. The speed after should be equal to just the new wavelength times. Actually, I'm just writing the same equation again. So I actually didn't even need this, so I can erase it and I can draw an arrow right here. All right, so same frequency, new wavelength, that gives new speed, and that gives the new tension. All right, that's the connection. Actually, this work is not needed for the tension, but it might be used for calculating the new fundamental if you want to. All right, so no one said anything. I made a mistake. What mistake did I make? Never follow bluntly what people say to you with the voice which sounds like people know what they say. Find the mistake. Cannot hear you. No. It's not about this, it's about this picture. You see, I looked at the picture and I said, oh, I made a mistake. If if it's related to a picture, it's related to the information which came from the picture. And information which came from the picture, of course, is information about the wavelength. This is the same string with the same length. What did I write? And what should be written? What should be written? Don't look at him. I'm asking you.
I am not sure.
Well, how does single wavelength look like? Exactly like it's in this picture. That is a wavelength. So in this situation, this, well, it doesn't change the logic. It just changes the number. That's it. Still, that's the new wavelength. And the new wavelength and old frequency gives new speed, and new speed gives new tension, and of course new fundamental also exists. But I don't want to do numbers because it's very similar to one of your homework problems. The source of tension might be different. We might change the tension by turning, how do we call it on the guitar? That thing we turn. If you don't know, how would I know? All right. Or we can change the tension by pulling on a string or by attaching a weight to it. So, all right, moving on. Now we have to talk about last subtopic of this topic, and then we move on to sound waves and Doppler effect. Driven oscillations, that means when, that happens when we use two sources. Each source generates a traveling wave. What's happening in between the sources depends on the sources. In general, nothing special happening, but if we tune it up, if they have same loudness, same amplitude, same medium, so same speed, and same frequency, in that case, we have to observe standing wave. We have to. And we could have done it mathematically, just by adding functions, or we can do it through a reason about the profile of that standing wave. There is one special point right in the middle between these two sources. We call them coherent, same frequencies, same phase. So two waves travel in space simultaneously from both directions. They overlap, and oops. Right in the middle, between these two sources, we should observe something specific. The question is, what? And so please keep entering. I'm going to use this moment to show, again, only two applets. So again, what I want to see is what kind of a type, what kind of a pipe is being used here. So wave travels, get reflected, and of course in real life, this and this happening in the same pipe or on the same string, but in order just to see it clearer, these pictures are separated. And now we can see, after they overlap, we observe. So what do we see here? Well, it's supposed to be clear antinode, but it's all kind of very old applet. Java is not very stable environment anymore. So, but still, they both move on left and right, so that's supposed to be a wave generated in a pipe or tube open at both ends. let's see what's going to happen here. A wave travels. See what weird thing will happen. Yeah, it starts reflecting before the wave actually travels, but that's an issue with the Java. But still, we can observe overlapping. Yeah, but probably there might be some phase shift now. Oh no, okay, I can see that this end is practically not moving. So that's supposed to be a model, but another end is moving. That's supposed to be a model of a pipe or a tube when one end is closed and one end is open. Too soon for that. Here, what did you say? Well, here we have to imagine two waves at the same time start running away, so they travel same distance over same time before they meet in the middle. And when they meet in the middle, let's say at t equals 0, we had like a bump here, so we should have, we call it crest, yeah, hill here, and they will travel toward each other with the same speed. When they travel exactly the same distance, that's a specific feature of this point, they should have the same direction. They should have the same displacement from the equilibrium always. Let's say it started from throw coherent speakers generating sound in phase should have the same wave orientation initially, so they would reach here again with the same displacement. So the total displacement, which is actually just the sum of two numbers, yeah, always will be, well, doubling, amplification of individual displacements, which means for this wave, we always have to observe an antinode right in the middle between the speakers. If we didn't have second speaker acting, that wouldn't be a case. Could have been anything. Yeah. That would be a reflected wave, and the reflection plus initial traveling wave might generate something depending on other conditions. But if the second speaker generates exactly the same wave but in opposite direction, right in the middle, we always must have an antinode. But what does it mean? It means that now we can very simply, clearly draw the actual profile, because, well, if this is an antinode, what should we observe? A quarter of a wavelength from it to the left or to the right. If we move away a quarter of a wavelength to the right, or a quarter of a wavelength to the left, what should we have seen right there? The node. But if we move another quarter of a wavelength from a node, we should observe another antinode, and then node, and an antinode, and symmetrical picture on another side. A node, an antinode, a node, an antinode. That's it. So we can draw a snapshot, a pictorial representation of such a wave like this. Well, eventually it should go to, I don't know, to the speaker, whatever happening at the speaker, we don't know. We can figure it out if I had numbers, okay, and if I knew distance. So this is a very important fact, which we can use for any driven wave. And we had two speakers yesterday, so I have them again. But now, first they have to face each other. And now, I don't really need two generators. Actually, I need only one. and they're supposed to be connected to the same generator. That makes them be coherent. Now, which is which? All right, I'm just going to plug both. It's faster than... Okay. So this is about 330 hertz. Well, if the frequency is 330 and the speed of sound is 330, the wavelength is supposed to be about 1 meter, a quarter of a wavelength about 25 centimeters. So right here between these two speakers, right here should be a maximum intensity. Yes, it's there. And if I move my ear left or right, I should observe the change in the in the loudness. Well, I could try to use a device which measures intensity, but again, only I could see it. So, what do we do? There is again a classical demonstration which you can find on YouTube, which helps us to see sound. How can we see sound? Well, we can use fire. So in this tube, I have two speakers. Let's check. What's wrong? Oh, I see what's wrong. So again, similar frequency, 330. How can we make fire? Where did I get it? No, lows. Now, of course, that's a requirement. I have to have it just in case every time when I use anything flammable. The pin is out. Okay. But so far, no. Well, if it's, oh, okay, I see something coming out. That's what wrong. Door. Ooh. So antinode, still too much blow. Node, an antinode, decrease, maximum, oh, again, disappeared. Somewhere here supposed to be node. So that's about 25 centimeters. Not very impressive, but visible. And now it should die out. Die. Power. Yeah, I didn't expect the wind through the room be so strong, but you get the idea. This is how we can make the sound be visible. Nope. I didn't bring my gloves today, but I have long arms. Lucky us, we didn't use it. We used it in PY 105, remember? For what? Adiabatic expansion. You don't remember? How couldn't you remember? Did you miss that lecture? The gas expands very quickly, so the temperature drops below freezing temperature, and we can see snowflakes, because there's always some vapor in air. So that's it. Well, and plus sound wave. All right, so this is a standard profile of a driven standing wave. And now, of course, we can answer the question about whatever happening between. The frequency was 330, and the speed of the sound is 330. So that automatically tells us the wavelength equals 1 meter. And now what can we do? Well, find the wavelength. The wavelength is equal to 1 meter. And what can we do now? We know right here we should have an antinode. Speakers 9 meters away from each other. So from here to here, we have distance 9 meters. So what's supposed to be the distance from the central or middle antinode to the closest node? A quarter, which means 25 centimeters. So 25 centimeters, then another 25 centimeters, etc., 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 etc. Right? That's how we should do it. So this is a half. That's all I need, 4.5 of a meter. And I can count how many quarters I could fit between the speaker on the right and the middle point. So that number is supposed to be equal to 4.5 over 0.25450 over 25. You should tell me the number, not him. Yeah. Hmm? 18? This is what you have to use. I don't see you using a calculator. Why? You should have your calculator handy. You could cancel fives, for example, but you could just do this. 18. Well, 18 quarters. So what should we have here? 1, 2. So every 2 we should have an empty node, 1, 2, etc., etc. 17, 18 should be an empty node. And 1, 2, 8. So 1, 2, 18. And of course, on the left side, we have to have exactly the same number of everything. So an empty node, a node, first quarter, second quarter, and now 18th quarter. That's it. And now we can count everything. We can count how many nodes, how many empty nodes are in between. We just have to see, the combination of nodes and empty nodes. And for the driven wave, we must start from the middle point because we always know we must have an empty node there. And that's it. Any questions? So you're going to do a very similar exercise in the lab. So now you know what to do. And we are done with this part. And we start the last part of the material related to the upcoming exam on Monday. A different room. I will send an email. It will be a different building, different room. Again. So this is what I wanted to show you before we move. First I want to switch to this. Now I want to switch to this. This is a model of a sound wave. Oops, so fast. Bless you. Okay, let's try one more time. One more time. So you would reset. So what do you see? You see a model of atoms inside, well, a wave, sound wave traveling away from a source. There's a source somewhere here, and molecules pushing each other, and we can see that average density changes, of course. When more atoms close to each other, density goes up, but also it changes the pressure. So a sound wave is a propagation of change of pressure. The average pressure, of course, is not zero. The pressure zero would mean no air, we would die. So that's not the case. There is average pressure. And sound wave is just oscillations of the pressure above and below average. That's it. That's what it is. And so this picture represents a snapshot of the change in the pressure above or below average. How do I know it's a snapshot? This, it's a distance. Of course, it's imaginary situation, but if we used a device like that, which could measure pressure very accurately, well, we could get a very similar graph. And of course, if we generate a standing wave, we call crests and throws, nodes and antinodes and between nodes. So everything is the same, but the sound waves travel differently in different media. So this is an example when we use this for a practical reason. So the question is, so let's see. You are observing a fisherman illegally catching fish by using a small explosive device to stun the fish. The explosion takes place near the surface of the water. Okay, so the sound wave travels slightly above the surface in the air and slightly below the surface in water. Relative to you, of course, it takes different time because they travel at different speeds. The question is, who are you? Why do you do that? Why would you be watching fishermen illegally catching fish? Do you make a documentary? Are you a policeman? Anyway, you're a physicist, right? The answer, of course, you probably already have it entered. It will travel faster in water because sound travels faster in more dense materials. That's it. It travels even faster in rails, for example, and still you hit the rail and you can hear it far away very quickly. And in this situation, we can actually find the distance from the explosion because we can measure the time difference between sound wave approaching to the microphone in water and sound wave approaching in air. That's actually how people can measure distances. So what do we do? Again, a picture. So, well, it has to be a bush because you're hiding behind it. What? I'm just having fun. So, fisherman, an explosion. So we have two sound waves, and this is how we describe the propagation of sound waves. In a minute, we'll talk about why. So it travels, this is what we call a wavefront, and wavefronts show distance, wavelength. So doesn't matter. In this situation, we have speed number 1 in air and speed number 2 in water. And they travel exactly the same distance, L. So what can we write? Well, we can write that this distance is supposed to be equal to speed in air times time it took to travel in air, but the same distance should be equal to speed in water times time to travel in water. And we know the time delay. And the question is this. Well, a delay is a difference. So what should we write? Time in water minus time in the air, or time in the air minus time in the water. If we do it correct, that's it. That solves the problem. If we do it wrong, we make a mistake. So what do you think? Oh, I gave away the answer here, right? If it travels faster in water, it takes less time. So the delay is the difference between longer time and shorter time. So that is wrong. That would have been a negative number. And that is correct. And now all we have to do is just solve two equations. This is the equation number 1, because speeds are given. And this is the equation number 2, because the time delay is given. And if we solve these equations, we can calculate time in air, we can calculate time in water, and we can calculate distance in the end. Yes, we can. Any questions? I'm not going to do that. That's a good mathematical exercise. Now, an explosion. Yeah? What does it mean? It means the source of sound has practically no size. So, a dot, a point. In this situation, as we know, the sound should travel in all directions away from the source, not just linearly. So, if we have a speaker, a spherical speaker which oscillates with a given frequency, it pushes on molecules with the same frequency, and the sound wave travels away, and if we could take a marker and mark, all points in a way which oscillate in phase, that would be a surface. That actually would be a sphere, and that sphere has a name. We call it a wave front. And those wave fronts travel, if the source keeps pulsing, those wave fronts travel away with the speed of the sound, and usually we picture the wave fronts spaced by a wavelength from each other. So this is a standard representation of a set of sound waves traveling from a point source, and this is a wavelength, this is a wavelength, this is a wavelength, this is a wavelength. And if we want to relate speed, wavelength, and frequency, that's equation which we always have been written. Now we have to make a very important statement. All of these variables must be used relative to the same person. We have it assumed, but now we have to say it out loud, because that person might not be at rest. That person might be moving, and that changes things. When a person I'll leave it for tomorrow. When a person and the sound source move relative to each other, well, that means I have 1 minute left, but I'm going to just finish the sentence. When a person, an observer, and sound source move relative to each other, the frequency of the sound experienced by an observer changes relative to a situation when nothing has been moved. And that phenomenon has a name, a Doppler effect. And tomorrow we're going to study the Doppler effect. And today we are done. Thank you very much. If you have any questions, send me an email. Go to Piazza, go to office hours. My office hours begin today, I think, at 1:30, but right now, teaching fellow should start office hours as well. And the lab, again, is in a different room, 136. 136, the lab room. Today and tomorrow. Good morning.